Hi there, this is Space Nuts. My name is Andrew Dunkley. Thank you for joining us for yet another episode. In this one, we are going to be looking at the latest with Boeing Starliner. They had trouble getting it off the ground. Now it looks like they're having trouble getting it on the ground. We'll be looking at coastal erosion, not on Earth, but on the only other body in our solar system where we know there is a liquid surface. And we don't know much about it, but they've come up with an idea about this particular place named Titan and what might be happening around the coast where you don't want to live. We're also going to find out about where you're most likely to form a moon, and dark matter and its influence is back in the news. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here to tell us all about moons and Titan and starliners and dark matter influence is Professor Fred Watson, astronomer at large. Hi, Fred.
Hi, Andrew. How are you doing?
I'm doing everything I can to stay warm. Our air conditioner died on Saturday afternoon, just as the temperature was dropping. So we've spent the weekend wrapped in blankets and 75 layers of clothing, and I don't know, we've killed a few geese and taken their feathers. We are freezing.
You've chosen the coldest weekend of the winter to do it, and it's not very pleasant. It's quite chilly.
Yeah, well, we just went past the winter solstice, so the shortest day, and it's rather chilly here at the moment. But we battle on.
Well, as you do, but I hope you get it fixed soon. Anyway, it's not very nice when your air conditioning's gone bung.
No, definitely not. Yes, gone bung. Yeah, the aircon's gone bung. That's what's basically happened. And you have a studio guest there who might make his presence felt sooner or later, named Geordie. So
yes, that's right.
We will welcome him.
He's at my feet when that happens.
Is he?
Yeah, having a bit of a snooze. So
good on him. Yeah. It's a tough life for dogs. Let's get started, Fred. Let's do a Starliner update. I remember when it wasn't so long ago they were trying to get it off the ground, and then they didn't, then they did, then they didn't, then they did, and finally it got up there to much fanfare, and now they're a bit stuck.
That's right. It is an interesting story, and one that I think what we're seeing is a very cautious approach by both Boeing and NASA to this, because Boeing contracts to NASA with their Starliner space capsule, which is designed to be the second kind of space taxi after the Crew Dragon, the SpaceX Crew Dragon, which has been successfully flying up and down with astronauts for quite some time now. But there was. So this is the first test flight, the first crewed test flight of the Boeing Starliner with two NASA crew members on board. It has flown twice before, I think, without crew and worked well. But there were issues before they left Earth, and I think it was the beginning of June when they headed up there. The return was scheduled for I think 14th of June originally, then the 26th of June, but now it's been postponed kind of indefinitely, although you can't postpone it completely indefinitely because you need to bring your astronauts back. And the reason is that there are issues with some of the thrusters, the maneuvering thrusters that the spacecraft has. It has, believe it or not, 28 of those, which is, it's quite a number, which I guess you need to position the spacecraft, to orient it so that it lines up exactly with the docking port on the International Space Station, things of that sort. But apparently 5 of the thrusters have got issues, which are apparently helium leaks, and the helium is something that pressurizes the thrusters. There's also an issue with the propellant valve, which is not moving as quickly as it should do. And so what they've done is put a hold on returning these astronauts back to Earth in the Starliner, and then try and fix these problems before it does make its return to the planet. I think there's a fairly full program of work for the astronauts up there while they're working while they're living at the space station. So they're not going to be sitting twiddling their thumbs, and quite a lot of what they might be doing, I suspect, is to do with getting back home. So that's the way the status quo at the moment. Of course, it could change very quickly. By the time this podcast goes to air, it may have changed already. But we wait developments with interest.
Yes, absolutely, and hope all is well. I know they're sitting there regretting that they didn't take their WD-40 with them. That would have solved everything, I reckon.
Well, it normally does. That's right.
Yes. Yeah, I think I've told you the story before about why it's called WD-40.
You have, but I'll hear it again happily.
Well, it was quite simply the 40th variation of the formula, and it's the one they got right. So,
yes, but doesn't the
WD-40
WD something to do with water dispersal or something like that?
Yeah, I'm going to look it up right now.
Good on you. You're somebody who can do more than one thing at a time, which I can't.
It's water displacement 40th formula.
There you go. So I was not too far off the mark. I do remember it being an issue that, the water was highlighted in the name.
Yeah. I don't know about helium disbursement, though. That might be another problem.
I think they're on about HD 95 now with the helium.
Maybe. All right. Fingers crossed for the Boeing Starliner. Look, they've done very, very well considering all the problems they've had before they got it off the ground for this crewed mission, and I'm sure they'll solve it. They're probably just being super duper cautious, and yes, that's fair enough too. Moving on, let's go to Titan, the only other place in the solar system or the universe, for that matter, that we know of that has a liquid surface. This is not a liquid surface that you want on Earth. We wouldn't be here if this existed on Earth in the capacity that it does on Titan, or we might be here in a different form. Who knows? But we're talking petrochemicals. One of the big mysteries of Titan is whether or not its oceans work the same way as they do on Earth, and they've been looking into this.
Indeed. And this is a question that goes back a long way. So remember the Cassini mission up to 2017 when it burned up in Saturn's atmosphere? An absolute treasure trove of information that came from it, including radar mapping of the surface of Titan, Saturn's biggest moon, second biggest moon in the solar system. And that radar mapping showed very clearly that, as suspected, actually, because people thought this was the case, there are seas and lakes on Titan which are of liquid natural gas, basically. The temperature at the surface is roughly minus 170 degrees Celsius. And that's cold enough for, these gases, ethane and methane, to be liquid. And so liquid natural gas on Titan fills these basins, which are mostly near the North Polar region. So the Titan's North Polar region has this whole array of lakes and seas, which show up dark on the radar reflections. They're actually, that's kind of how we know that they are very smooth, because the radar just bounces off them. It doesn't scatter like a rough surface does. But the question has always been, are there waves on those lakes and seas? And there's two schools of thought here. One is that they are very smooth. And in fact, I do remember being staggered to read once, this is quite some time ago, probably a decade ago, that the biggest wave height on Titan seas was probably 1 millimeter. And that seems, not there's not much surfing with millimetre high waves there.
Not unless you're a flea.
That's right. Not unless you're a flea. Yeah. So the other side of the coin, though, was that occasionally on Titan, you get bright patches being reflected in the radar beams. And those bright patches are something that come and go. They don't stay. They're not permanent. They don't last very long. And so one suggestion for that was that these were wind-driven waves. You got storms, basically, that drove the waves on the surface of Titan. Another thought was possibly methane icebergs.
Didn't we talk about that once? That rings a bell.
We did, yeah. And maybe the methane icebergs hang around for a while and then melt or disappear. And so that's why these bright things that appeared in the seas are temporary. They come and go. So a group from a number, there's a lot of NASA scientists in this, scientists from MIT, Massachusetts Institute of Technology, and other institutions. US Geological Survey is also involved with this work. What they've done is taken a different approach. They've looked at the shape of the coastline of these lakes and seas because they're quite intricate coastlines. If you look at photographs of them, it's pretty easy to find them. You can see river estuaries and headlands and all of that sort of thing, the kinds of things that we just think of as being natural coastal features. So they've looked at those in detail, and taking the Earth as a model, they've said, okay, on Earth, there's two main kinds of erosion of a coastline. One is what's called uniform erosion. And that occurs where the coastline is actually being dissolved away by whatever chemicals are in the water. And we see that in karst country, where you've got limestone with lakes forming in it. And basically, the water in the lakes dissolves the limestone. And so you get this what's called uniform erosion. And the other kind is wave-driven erosion. And wave erosion depends on the wind direction, the wind speed that causes the waves. But the interesting feature is that these two different sorts of erosion, uniform erosion, wave erosion, give quite different styles of coastline, if I can put it that way. They wear things down differently. And so the analysis of the Cassini images have essentially supported the idea that these coastal features are wave-driven rather than uniform erosion.
How interesting.
Yeah, so it's a really neat way of trying to work out whether there are waves on the seas of Titan. And it looks as though that's confirmed as being a possibility.
If there are waves, that means there must be something driving them. That'd have to be wind, wouldn't it?
Yeah, that's right. And the next step in this research is to try and, by careful analysis of these coastal features, try and work out what the wind direction is and what speed it is, the prevailing winds on Titan.
But the surfers that listen to us are now very excited to learn of. But that minus 170 degrees, you'd need a heck of a wetsuit.
Yeah, and you wouldn't want your air conditioning to break down either.
No, definitely not.
There is just one postscript to that story, though, and that is that come 2028, we hope, NASA will launch its Dragonfly mission, which is an autonomous rotorcraft, a drone, basically, which will be in orbit around, or it won't be in orbit, it'll be patrolling the landscape of Titan. Hopefully we'll land on a beach somewhere and actually have a look at these waves and tell us what the waves are like. So yes, Dragonfly is something very much to look forward to, the next big mission to Titan.
Yeah,
I don't know how long it will take to get there, but I think it's quite a while. So 2028 launch might be, might be 10 years before it gets there, but at least it's on its way.
I'm going to find out.
Okay, good, because we need to put it in the diary for Space Nuts for when Dragonfly is deployed on Titan.
And yes, July 2028, 6 years to reach
Oh,
Titan.
okay, not bad. So 2034, yeah,
Yeah.
we'll still be going strong by then. That's only a decade away. Yeah.
Absolutely. Yeah, not a problem at all. If you'd like to follow up on that story about the waves on Titan, you can find a fabulous write-up at universetoday.com. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, let's talk about moons and where to find them. And, well, it looks like, we've got one. Mars has got a couple. Venus doesn't have any, does it?
No.
But they're starting to think that the formation of moons is more likely around rocky planets. What's the story here?
Yeah, so let's just review what we know about the origin of our own moon. The current theory about the origin of the moon is that a Mars-sized planetesimal by the name of Theia, we've given it a name even though it's long gone.
It doesn't exist anymore.
That's right. It collided with the moon very early in the history of the solar system. You know, the solar system might have only been 10 or 100 million years old at that time, which is very, very new. You're forming planets, you've got these planetesimals charging around all over the place. And this collision is thought to have occurred very early on, which excavated an enormous amount of material from the Earth. Basically, the amount of energy that was put in rendered the surface of Earth molten, so it became a lava world. And the debris basically formed a ring around the Earth, which eventually accreted to become the moon that we are familiar with today. And so that is the basic picture. There's still a lot of, cases where the jury's still out on the angle, velocity, all of those things, the exact mass of Theia. By the angle and velocity, I mean of the collision that created the moon. So this apparently, when you look at these studies, if you've got a high energy impact, what you wind up with, and this is the theoretical study, is a disk around the planet that's dominated by vapor, where whilst or a sort of gaseous material, if I can put it that way, while a lower energy impact, you get a disk that's dominated by rock, basically by dust, silicate dust. And so which of those happens apparently will play a big influence on what you get at the end of it, whether you get a moon or whether you just get vapor, that, gaseous material that just disperses into space. And apparently, and this is a kind of technical term that I've not really been that familiar with, but it's something called a streaming instability. Get it right, friend. A streaming instability, which is the deciding factor in what you're going to get. So the streaming instability comes depending on the velocity of the impact, the energy of the impact, and it turns out that the bottom line, as you've probably picked up from what I've been saying, is that the more the less high velocity, the lower energy, perhaps you could say a gentler impact, that is more likely to result in the formation of a large moon. Whereas if you've got a high energy impact, you don't get the moon, you just get a lot of vapor, a lot of gas that heads off into space. So it's an interesting suggestion. And it sort of somehow, to some extent, it reinforces our view that perhaps many of the moons of the outer planets, the gas giants, which are much smaller than the parent bodies, unlike our own moon, which is is pretty substantial compared with the parent body. It's 1/80th of the mass of the Earth. It's why, it tallies with the suggestion that some of those larger planets have moons that were really caused by perhaps captured material or colliding comets, colliding asteroids, things of that sort, rather than a collision process like the one that we think formed our own moon.
No, that's interesting, because you look at Mars, and the two moons of Mars seem to be more likely captured objects.
That's correct, yes. We don't really know too much about the origin, Phobos and Deimos. They probably are captured objects rather than something caused by an impact like the one that caused our own. I mean, it sort of, emphasizes the point, really, that maybe our own moon is quite a rarity, because it's not uncommon for smaller bodies to have large moons, and the case in point is Pluto, the dwarf planet Pluto, with its moon Charon, which is, I can't remember, it's significantly high. I think it's something like 1/6 of the mass of Pluto. I might be exaggerating that. I'm just trying to remember from the New Horizons flyby, but it is quite big compared with Pluto itself.
It's 1,214 kilometers across,
which is about
Charon.
half. Yeah, half the diameter of Pluto. Pluto's a bit more than 2,000 kilometers.
Yeah.
So yes, it's there you've got two bodies which are similar in size, and they're almost a binary body. And we know there are binary asteroids. We see many binary asteroids, pairs of asteroids. So when you get to the smaller end of the planetesimal or planetoid spectrum, it seems that large moons are more common. But when you grow up when you look at bigger planets, bigger objects in the solar system, it looks as though smaller moons are the way it goes. So the suggestion of this particular piece of research is that perhaps small rocky planets are better at making moons than large ones. It comes from a variety of scientists, mostly in the United States.
That's fascinating. Well, I suppose now, if they like, because they've been doing simulations to try and prove their theory, what they probably need to do now is take a look out there and see. It's probably very difficult. Finding an exoplanet's hard enough, but we're getting better and better at it. But finding moons around those planets, if this theory holds true, you probably have better target options. But as we've said before, seeing a rocky exoplanet is much more difficult than a gas giant, isn't it?
That's right. I think there's one or two suspected moons. There's nothing, that's been guaranteed an exomoon. And one of the things that comes to mind, and we might have talked about this a year or so ago, is with gravitational microlensing. This is where a star with planets passes in front of another star in the background, and the gravitational field of the foreground star distorts the background star and magnifies it. It actually makes it much brighter. And you can detect planets that way, quite small ones, actually, much smaller than the other normal planetary detection methods. And I think there was a suspected exomoon found in one of the microlensing experiments that was done a few years ago, if I remember rightly.
Except I think, correct me if I'm wrong, but haven't they got to see it 3 times to prove it?
Yeah, except you don't with microlensing. It's a one-off. You're absolutely right, because you never see the star or the planet again. They're all invisible. So it just gets a microlensing event name rather than a planet name.
No, fair enough. Yeah, interesting. All right, if you want to look at that story, space.com is the website where you can check it out. To our final story, Fred, and this is a pretty big one, actually, and not surprisingly, dark matter is in the news again. But we're looking at the influence of dark matter, and it's again questioning our understanding of the universe and why things are happening the way they are.
That's right. So we've, we return to this theme so many times and so often, but it is interesting. It is a huge part of current astronomical research. What is the nature of dark matter? And some people question whether it really exists at all. And so this is some research that's come out of Case Western Reserve University in the US. And it goes back to one of the methods that was used in the early days of dark matter research to determine what was going on. Just to give you a bit of history, Andrew, dark matter was first postulated actually back in 1933 by a very interesting astronomer, Swiss-American astronomer by the name of Fritz Zwicky. And Zwicky was observing galaxies in a cluster of galaxies called the Coma Cluster, the northern constellation of Coma Berenices. And he worked out that if all he could see was all that was there, these galaxies should have gone their own separate ways millennia ago, because there wasn't enough mass that he could see that would hold the cluster together. And it was then, nobody understood that, so it was just ignored basically as a curious fact of astronomy that we couldn't explain. And it wasn't until actually 1970 that it was raised again by an Australian astronomer, Ken Freeman. I was in touch with Ken last week. He's still going strong. He got the Prime Minister's Science Prize for this work. But not back in 1970, he said that the galaxies that he was measuring, he was looking at the rotation of galaxies, were going too fast to stay together. They should fly apart. And that was then confirmed later in the 70s, 1978, by Vera Rubin, a wonderful American astronomer. But she basically put together all these ideas to work out that the only way you could get galaxies holding together was if they were enveloped in a sort of spherical cloud or halo of dark matter. And that's been the sort of status quo ever since. But we now have this new research, which
this is a big part.
That's right. It takes the rotation idea, but looks at the way galaxies rotate millions of light years from their centers. In other words, the very outer regions of galaxies, they are basically, sorry, I've just cancelled a call there from somebody quite famous, interestingly. So said I'll call you later. They've looked at large galaxies and looked at the way they rotate in their outermost regions and discover that it looks as though they're still being controlled by dark matter. So the bottom line is that they're saying that the dark matter halos, either the dark matter halos are much, much bigger than we thought they were, that these galaxies are immersed in enormous halos of dark matter, much bigger than we thought they were before, or we've got it wrong. And, that we're misleading ourselves by the fact that our understanding of gravity and acceleration are incomplete. And this goes back to Mordechai Milgram's theory of MOND, as it's called, modified Newtonian dynamics, that says that at very low accelerations, Newtonian dynamics doesn't work the way Newton said it did. In other words, you push something and it moves, but it doesn't quite work that way at very low accelerations. So that's the issue. It's once again, it's challenging dark matter. Dark matter, the mainstream belief is that it is some form of massive subatomic particle that we have not yet discovered. In fact, the subatomic particle fraternity have worked very, very hard to try and find whatever this is, but we've failed completely. So if it's not a particle, what is it? And this work kind of pushes back in the direction of our understanding of acceleration being wrong.
Yeah, I think it's WD-39. That's what it is.
Yes. Well, there you go.
Could be. It is. Look, I'm hoping the day will come where we find out what dark matter is, and the penny drops, and we go, oh, yeah, of course, it's so simple.
Yeah. Yes.
We're not there yet.
No, we're not. And the reason why MON doesn't have a big following is that it sort of lets you down in other ways. It might explain the rotation of galaxies, but it can't explain the behavior of galaxies in clusters, which is what old Fritz Vicky was discovering. And there are a few other things that don't work well. In fact, to do with the general structure of the universe, you seem to need dark matter to make the universe look like it does. So the dark matter's still got a lot going for it, Andrew.
Yeah, sure has. And of course, now that we've talked about it, I'm sure we'll get one or two questions. And potential theories. A lot of our audience do put up theories, which we do like.
We do.
Okay, if you want to read that story, it's at spacedaily.com, and you'll probably find it on many other pages as well. That brings us to the end of this episode, but don't forget to visit our website, spacenutspodcast.com or spacenuts.io, and have a look around. Don't forget to become a member. If you're interested in becoming a member of Space Nuts, you can do that on our website. You can click on the supporter link and learn about becoming a patron, and we do thank our patrons very, very kindly for supporting us financially. We don't ask for that, but the fact that you're willing to do so is very humbling indeed. And everything else you need to know about us is on our website as well. And don't forget about our social media platforms as well, including YouTube. And if you do listen or view on YouTube, hit the subscribe button if you haven't done so already. That's it, Fred. Thank you so much.
Great pleasure as always, Andrew. It's it's becoming quite regular, this, isn't it? It's quite nice to do it. Yeah.
It's almost like we've been doing it for years.
For years, yes.
Yeah. All right, thanks. There's more. Okay, thanks, Fred. We'll see you soon.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and Hugh back in the studio, who's trying to figure out how to use the internet. And from me, Andrew Dunkley, always good to have your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.